Today, we are breaking down cocktail shaker sort, one of those algorithms that looks simple, but gives you a lot to talk about in DSA interviews.
Exactly. And the best way to understand it is to compare it with bubble sort. Bubble sort walks only one way, left to right.
Standard bubble sort is like checking traffic on a one-way road. It scans the array strictly from left to right, pushing the largest values toward the end.
But that creates a problem, right? What happens when a small value is stuck near the end?
That small value becomes a turtle. It inches left only one position per full pass.
So that is the turtle bottleneck.
Exactly. Cocktail shaker sort solves this by opening a two-way street.
So instead of only moving left to right, it moves left to right and then immediately right to left.
Cocktail shaker sort says, why stop there? It shakes the array from both sides.
That explains the name. It is also called shaker sort, or bidirectional bubble sort.
The core idea is still tunnel vision. The algorithm only compares two neighboring elements at a time.
That means it looks at A at index I and A at index I plus 1. If the left value is bigger, we swap.
Large values behave like rabbits. They jump quickly toward the right.
And small values behave like turtles. But this time, the backward pass helps them crawl left much faster.
Let's now set up the sorting engine and walk through the pseudocode line by line.
Line 1 is cocktail shaker sort, taking A and N as input. This function takes an array A and its size N.
Line 2 is start gets 0. This sets the left boundary of the unsorted part of the array.
Line 3 gets N minus 1. This sets the right boundary of the unsorted part.
These boundaries tell the algorithm exactly where the unsorted data lives.
Right. And as numbers lock into their final positions, the active search area becomes smaller.
Line 4 is swapped gets true. We set it to true at the beginning so the while loop can start.
Line 5 is while swapped equals true, do. This means the algorithm keeps running as long as swaps are happening.
And if swaps stop happening?
Then the array is sorted. No swaps means every neighboring pair is already in the correct order.
Line 6 is swapped gets false. Before each pass, we assume no swap will happen.
And if a swap does happen, we flip it back to true.
Line 7 is the forward pass comment. Move the largest element to the right.
This is the rabbit move. The big number runs toward the right end.
Line 8 is for I from start to end minus 1, do. We scan from the left boundary toward the right boundary.
And we stop at end minus 1 because we compare A at index I with A at index I plus 1.
Line 9 is if A at index I is greater than A at index I plus 1, then. If the left element is greater than the right element, they are in the wrong order.
Line 10 is swap A at index I with A at index I plus 1. So we exchange those two neighboring values.
Line 11 is swapped gets true. This records that the array still needed work.
That one Boolean flag is small but powerful. It prevents wasted computational cycles.
Line 12 is if swapped equals false, then.
Line 13 is stop.
If a full forward pass finishes with no swap, the data has already achieved total order.
So the algorithm breaks immediately instead of scanning back and forth for no reason.
Line 14 is end gets n minus 1. After the forward pass, the largest value has reached the right side.
So we shrink the active sorting window from the right. That final slot is already sorted.
Line 15 is swapped gets false. Now we reset the flag before the backward pass.
Line 17 is the backward pass comment. Move the smallest element to the left.
This is the turtle rescue mission. The small values get pulled back toward the left.
Line 18 is for I from end minus 1 down to start, do. This loop moves from right to left.
Line 19 again checks. If A at index I is greater than A at index I plus 1, then.
Line 20 swaps the two values if they are in the wrong order.
Line 21 sets swap to true if a swap happens during the backward pass.
Line 22 is start gets start plus 1. After the backward pass, the smallest value has reached the left side.
so we shrink the active sorting window from the left too.
Line 23 is return A. Once the loop ends, we return the sorted array.
Nice. Now take a look at this 6-element unsorted array. 5, 1, 4, 2, 8, and 3.
Here, n equals 6, so start equals 0, end equals 5, and swapped equals true.
Round 1 begins with the forward pass. We scan left to right across the array. 5, 1, 4, 2, 8, and 3.
At I equals 0, compare 5 and 1. Since 5 is greater than 1, they swap.
The array becomes 1, 5, 4, 2, 8, and 3.
At I equals 1, compare 5 and 4. Since 5 is greater than 4, swap again.
Now the array is 1, 4, 5, 2, 8, and 3.
At I equals 2, compare 5 and 2. Since 5 is greater than 2, swap again.
The array becomes 1, 4, 2, 5, 8, and 3.
At I equals 3, compare 5 and 8. No swap because they are already in order.
At I equals 4, compare 8 and 3. Since 8 is greater than 3, they swap.
Now the array becomes 1, 4, 2, 5, 3, and 8.
With that single sweep, the absolute largest element, 8, is securely locked into its correct final position on the far right.
The rabbit made it to the finish line.
Since swaps happened, swapped is true, so we do not stop.
Then we shrink the right boundary using end gets end minus 1. So end becomes 4.
Now the algorithm immediately reverses direction for the backward pass.
The current array is 1, 4, 2, 5, 3, and 8.
The loop goes from I equals 3 down to 0.
At I equals 3, compare 5 and 3. Since 5 is greater than 3, swap.
The array becomes 1, 4, 2, 3, 5, and 8.
At I equals 2, compare 2 and 3. No swap.
At I equals 1, compare 4 and 2. Since 4 is greater than 2, swap.
Now the array becomes 1, 2, 4, 3, 5, and 8.
At I equals 0, compare 1 and 2. No swap.
This reverse sweep drags small values toward the left side.
And now 1 is locked at the starting position, while 8 is locked at the ending position.
In one bidirectional round, both extremes are handled.
Exactly. The unsorted operational window is compressed from both sides at once.
Then we do start gets start plus 1. So start becomes 1.
Now round 2 begins.
The current array is 1, 2, 4, 3, 5, and 8.
The current boundaries are start equals 1 and end equals 4.
That means index 0 and index 5 are already outside the active search area.
Before the forward pass, we reset swapped to false.
Now I goes from 1 to 3.
At I equals 1, compare 2 and 4. No swap.
At I equals 2, compare 4 and 3. Since 4 is greater than 3, swap.
The array becomes 1, 2, 3, 4, 5, and 8.
And that is already sorted.
At I equals 3, compare 4 and 5. No swap.
Since one swap happened in this forward pass, we do not stop yet.
Then we shrink the right boundary again. End gets n minus 1, so end equals 3.
Now we reset swapped to false before the backward pass.
The backward loop goes from I equals 2 down to 1.
At I equals 2, compare 3 and 4. No swap.
At I equals 1, compare 2 and 3. No swap.
0 swaps in the backward pass.
Exactly. So swapped remains false.
Then start gets start plus 1. So start equals 2.
Now the while condition checks whether swapped equals true.
But swapped is false, so the loop ends.
And the final sorted array is 1, 2, 3, 4, 5, and 8.
So the algorithm sorted the array by shaking it from both directions.
Forward pass pushes large values right. That is the rabbit move.
Backward pass pulls small values left. That is the turtle move.
And tunnel vision means it only compares 2 neighboring values at a time.
But wait, is cocktail shaker sort always much faster than bubble sort?
Not always. The best case time complexity is big O of n. thanks to the early exit flag.
And the average and worst cases are still big O of n squared because we still have nested loops.
So it clears the turtle bottleneck faster than standard bubble sort, but the mathematical limits remain the same.
It is also in place, using only big O of 1 extra memory.
And it is stable, meaning equal elements keep their original relative order.
In a visual diagram, you can think of 3 logic zones.
The first zone controls the outer loop and the swap flag.
The second zone drives the forward pass and shrinks the right boundary.
And the third zone drives the backward pass and shrinks the left boundary.
That is a clean interview explanation.
For interviews, remember this. Bubble sort checks traffic on a one-way road.
Cocktail shaker sort opens a 2-way street.
Bubble sort walks one way.
Cocktail shaker sort dances both ways.
Final takeaway. Compare neighbors, swap if needed, move right, move left, shrink the boundaries, and stop when no swaps happen.
If this video made the concept easier for you, please hit the like button, subscribe to Descentio, and turn on notifications. Thanks for watching, and I'll see you in the next video.